Hello everyone. Today our group will talk about the topic angular momentum, and this is members of our group. First, I'm Vu, and I'm gonna talk about the angular momentum of a particle. The angular momentum is defined for a particle of mass moving with translational momentum p. L equal r times p, where r is the position vector of the particle pointing from the origin of the coordinate system to the particle. The angular momentum is defined in terms of the motion of a single particle that does not need to be orbiting the origin of the coordinate system. In fact, the particle does not even need to be moving in a curved path. A particle does not need to be in orbit around the z-axis to have angular momentum around that axis, because angular momentum can be determined by using the vector cross product. Its direction can be found by using the right-hand rule. As you can see in this picture, the vector L must be perpendicular to the plane containing the vectors r and p. As with any cross product, the magnitude of angular momentum may be found from L equal R times M times V times psi phi, where phi is the angle between R and P. L is 0 when R is parallel to P. Phi equals 0 or 180 degrees, and L equals M times V times R when R is perpendicular to P. Phi equals 90 degrees. These SI units of angular momentum are kilogram times meter square. The vector sum of and torque acting on a particle is equal to the time rate of change of the angular momentum of that particle. The fact that a vector crosses into itself is zero. From Newton's second law and the definition of the net torque, delta L over delta T equal the torque net. Now I will talk about the angular momentum of a rigid body. We can find an expression for the angular momentum of a rotating rigid object by considering it to be a collection of particles orbiting the common rotation axis. For a system of particles making up a rigid body, all the particles travel in circles and the magnitude of the total angular momentum is L equal I times omega. The angular momentum L is in the direction of the angular velocity vector omega. The direction is given by the right-hand rule. For linear motion, the change in total linear momentum of a system is related to the net external force by F net equal to delta P over delta T. And for rotational motion, the change in angular momentum of a system is related to the net torque by torque net equal to delta L over delta T. And next, we will introduce you about the analogies between linear and angular momentum and energy.
Hi, my name is V. I am going to introduce you about the conservation of angular momentum. The conservation of angular momentum is a physical property of a spinning system so that its spin remains constant unless it is acted upon an external torque. Put another way, the speed of rotation is constant as long as the net torque is zero. It is also one of the four exact conservation laws in physics, which state that a specified property of a given system remains constant as that system evolves over time. There is another way for that law is where when there is no external torque act on an object, there is also no change of angular momentum will occur. The net external torque acting on a system of particles is equal to the time rate of change of the system total angular momentum. It will be expressed as the Newton's second law. Thus, the system total angular momentum is equal to the total external torque exerted. This equation holds for a single particle, a collection of particles, or an object. If a single particle moving along a straight path, the net force F net is on the particles will speeding up along that path. When no net force acts on the system translational momentum is conserved. According to the previous equation, then we have the net external torque acting on the system is zero, and the system's total angular momentum at that time is will conserve. If the angular momentum of a particle is conserved, then we have the radius initial time to the momentum, the linear momentum as in initial will equal to the radius final time to the momentum final. If the angular momentum of a rotation object or collection of particles is conserved, it can be written as the moment of inertia, which is at initial time to the angular speed at initial, will be equal to the final inertia moment of inertia time to the angular speed. Mm, one example of conservation of angular momentum is a person holding a spinning bicycle wheel on the rotating chair. The rotating chair. In the first case, a person holds a spinning bicycle wheel, and the angular momentum of the wheel is shown as this. And in the B case, the direction of the spin is reversed and causing the person to spin on the chair to conserve the angular momentum as well. Initially, the wheel has an angular momentum in the upward direction. When the person turns over the wheel and the angular momentum of the wheel reserve direction below because the person wheelchair system is an isolated system, total angular momentum must be conserved, and the person begins to rotate in an opposite direction as the wheel. The vector sum of the angular momentum in A and B is the same, and the momentum is conserved. Hi, my name is Hoa. As we already introduced about the conservation of angular momentum, now we can answer the question based on the angular momentum. That's why does the Earth keep on spinning? What started its spinning to begin with? And how the ice skater managed to spin faster and faster simply by pulling her arm in? And why does she not have to exert a torch to spinning faster? The rotational analog will answer that question. So by now, the pattern is clear. Every rotational phenomenon has a direct translational analog. It seems quite reasonable to define the angular momentum L as L equal moment of inertia multiplied with the angular speed. So at the same time, the momentum of linear motion is defined as the momentum equal the mass multiplied with the velocity. So at the angular motion, the net torque is the vector sum of all the torques acting on the object. The total mass equal the moment of inertia multiplied with the angular acceleration. The angular acceleration are the product of the net torque with inertia opposing acceleration. This is the rotational analog of acceleration equal the total force, net force divided by the mass. At the same, the mass that the angular acceleration are defined as acceleration equal the total net torque divided by the moment of inertia. The angular momentum and the linear momentum are quite the same. The angular momentum of a system is conserved if there is not net torque, whereas the linear momentum is conserved if there is no net force. Angular momentum is completely analogous to linear momentum. It has the same implication in terms of carrying rotational forward, and it is conserved when the net internal torque is zero. Angular momentum, like linear momentum, is also a property of the atom and subatomic particles. Here is some formula that's using analogy between linear and angular momentum and energy. So at linear motion, the final velocity equal the initial velocity plus the acceleration time, the change of time. And same thing that in angular motion, the angular speed, the final angular speed equal the initial angular speed plus the angular acceleration time, the change of the time. Here is the angular displacement or the rotational angle. Is equal the initial speed, angular speed time the time plus 1/2 the angular acceleration time the time square. And in linear motion, the displacement equal the initial velocity time plus 1/2 acceleration time square. And to find another way to find the final angular speed is the final angular speed square equal initial angular speed square plus 2 angular acceleration time the angular displacement or the rotational angle. As in linear motion, the final velocity square equal initial velocity square plus 2 acceleration time the displacement. So the angular motion and linear motion are analogous and have the same. Thank you for watching our video project. I hope after this video you will have some idea about the conservation of angular momentum. Thank you.